I will speak about modules and how you can use them today on multiple platforms. I will give you a short recap about the current state of what you need to know about modules. This is not a full introduction. If you're expecting an introduction into modules, this is not a talk here. I've started talking about modules in 2019. If you want to know all the details about different aspects of modules, look at my previous talks from 2019, 2020, 2021. And this is what you probably should know to understand everything what I will be talking about. Then I will talk about compilers and the current state of implementations, about modularization, about build systems, module dependencies and how you can handle them. And I will give you a short demo. As you can see, I do stuff for quite a long time. If you want to take a picture of this QR code here, this is where you can find the slides beginning from possibly tomorrow, and also all of the demo code that I will be showing. Just a quick question. Who of you has heard about modules beside the title here? Good. Who of you have actually done something with modules? Okay, we can improve. Who of you have modules in production? Wow, more than I expected. Now we have 3 people. This is good. And all of the rest start using it. Okay, just to make sure that we are all on the same page, I give you a short recapitulation about what modules are about, and this is probably the shortest introduction to modules that we will ever see. This is a traditional code here. On the right we have a library with a library interface header and also with an implementation file. And on the left we have a translation unit of your code, also a translation file. And as we all know, there's a barrier between translation units. Every translation unit is independent of all others. So this means the interface becomes incorporated into each translation unit, which means because of the point why you actually include an interface of a library into a translation unit, the meaning of the text that you have been writing into your header may change. And this may also cause subtle ODR violations that you're probably not even aware about. So what does the compiler do if it compiles a translation unit? It starts out with a known compilation state at the beginning, no declarations, a couple of macros, a couple of compiler options. And during the compilation of the translation unit, the compiler will possibly know more macros, in particular a lot of more declarations. And at the point where the library interface header is included, the compilation state is no longer the same as it has been in the beginning. And this can change the meaning of your code. And you probably don't know it. It's not only the macros, it can be more things that can affect the semantic meaning of your interface. Well, at the end of the compilation, the compiler writes out the object file, we all know that, but everything else is discarded. If we go to modules, one important thing changes. The interface is no longer a header that is textually included into other translation unit, it becomes a translation unit on its own. And this has an important change in the behavior. The library interface unit becomes compiled. So now it is also separated and isolated from all other translation units. This sounds weird because now how to transport the declarations from the interface to other translation units? Well, there's a new channel now, and this new channel is called BMI, Build Module Interface. This is an additional artifact that becomes included into the implementation of your library and also to all users that want to import the interface of a library. The difference is within the module itself, the implementation files of a module see everything that's contained in the interface translation unit, but the users outside of a module see only parts of it, and this is done by explicit export statements. So the architect of a library decides what becomes available on the outside of a module. For the compiler, there's not that much difference here, but there's an important difference. And the important difference is the translation unit is the module interface is a translation unit on its own, so it starts out with a known compiler state. You totally know what the semantics of your interface are. And at the end, we don't get only one build artifact, we get two, both the object file and also the BMI file with all the contents of the declarations and definitions that the compiler has seen during the compilation of the interface unit. And it also, usually at least, contains information about the initial compilation state. So now we have actually means to check for compatibility between the compilation of an interface in a library and the usage of an interface. This is a pretty dense picture here, but we need to tell and learn about some important things in modules. In the top half of this slide here, we have the primary module interface unit. This is what I've been speaking about before. And at the bottom, we have the module implementation unit. And both of these translation units of a module have a name. Hence the name, this is a named module. You can refer to other modules by using the names, and this is the only way to refer to modules. Then we see this greenish part on the slides. That this greenish part belongs to both the module interface and both to the implementation. And these sections of the translation units comprise the so-called module purview. Module purview means everything that is in these greenish sections of the code belong to the module and only to the module. And then there's also this brownish section, the pieces here. These are the sections in the translation units that belong to the so-called global module. In the beginning you said you're not using modules. You actually do. Since 40 years possibly, since the inception of C++, everything that you have written so far belongs to the global module. This is a module that has no name, and as you can see, every module translation unit can also have parts that belong to this global module, the thing from the past. This is where all your existing code lives, and everything what you want to use in your module is part of this legacy world of traditional compilation, and this applies, for example, to the standard library. The standard library belongs to the global module. and also all of the libraries and the code you have written in the past, everything belongs also to the global module. And if you want to use these parts in your modules themselves, you have to place the interfaces in here. The global module is a module without name. So what does it mean to export things? I've said before, everything the compiler sees in the library interface becomes incorporated into the BMI, but only the parts that we actually mark as an export, like here, is actually available to the users. Here I have a function definition called frop, and its declaration. The only thing that changes using the export keyword is that the name frop becomes visible to the users of a module. This is the only change that the keyword does. In the implementation, you also have a module declaration with the same name as in the module interface unit. And this is the key takeaway from all what modules are about. There is one important thing that you need to know about the module purview. The module purview is the means that you get an important feature of modules. And this is name isolation. What does it mean? We have two modules here. Module 1, top left, module 2, top right. Both of them have a function definition called foo, with the same signature, in the same namespace, and you usually would assume these function declarations refer to the same entity, the same function foo. Because these two function declarations are in the purview of their respective modules, these are now two different functions called foo. So if you write a library, you no longer have to think about where do you place my internal stuff. You no longer need unnecessary namespaces, and you don't have to fear that you come up with a name that possibly is already existing in your program. Each of these two functions foo are different entities. So if you import both of these modules and use functions from the interface that refer to the respective functions foo in the implementation, each call of the functions bar and bus here in this example refer to their respective independent foo implementations. And the linker can also tell them apart. The reason is that everything in the module purview is attached to the respective module they're in. So instead of just calling this a foo, this is a foo function attached to module 1 and also a function foo attached to module 2. These are two different entities. And you get two different symbols for the linker. This is one of the key features of modules. Then there's another thing. Modules are not just a single entity with one interface, translation unit, and implementation units. Actually, named modules can be composed from parts. In fact, we have 5 different options to choose from to compose a module. And besides the named module composition, you can also have a thing that I've not been speaking about yet, and this is the header unit. A header unit seems pretty simple. You just take an existing header, give it to the compiler with a certain flag, and the compiler would compile your header up to translation phase 7 into Just like as it is a translation unit, and you get an object and a BMI file. But there are key differences here. Everything in named modules, all these translation units have a module per view, and so they belong to the respective module. Header units don't. Everything in a header unit belongs to the global module, so you need to be careful with selecting your names. In the named modules, you can possibly have sections of the global module, but the header unit is completely part of the global module. And another important difference between named modules and header units is the capability of exporting macros. Header units do. They behave in this regard just like an include, but named modules have no way of exporting macros. If you have library interfaces that use macros, you can't do that with modules. You need to find different solutions. And this ability or inability of exporting macros gives named modules full isolation. They can't be affected by other code, and they don't affect other code, whereas header units can. So this is a short introduction into modules. I don't go into any details. You can see or can look at the talk from 2019, 2020, and 21. And these 3 talks will give you everything you need to know about the stuff that I've been talking so far. Now it becomes more interesting. Let's speak about the implementation status of compilers. How are we today? And where are we? I will give you some information about the features that the different compilers support, how complete the implementations are, and the hot topic of file extensions, and the maddening part about compiler flags that each compiler requires. And this is not my opinion, this is the opinion of the implementers. This is what they tell about their compilers and how they document it. And this is the current situation. If you have seen one of my prior talks, you had a similar table in there, but now you will notice over the course of the past 2 years, the table is mostly green. Wonderful. Who would have expected that? Besides bugs in the implementations, MSVC is feature complete for quite some time now. It doesn't mean it doesn't have bugs, quite a lot of them. The same is true with Clang and GCC. The problem is both Clang and GCC only still have partial implementation of some key features. But besides that, you can actually do interesting stuff with both of these compilers. All compilers have converged on the same model how name attachment works. This is good. You don't have to do different things for different compilers. The major difference lies in the current implementation state of a modularized standard library. MSVC has one. Clang, libc++ also has one, but it's still in an experimental state. I'm looking forward to see more about this in the near future, possibly Clang 18, if I'm right. Well, here we have the libc++ leading developer, or one of them at least. I'm really looking forward to see what we get in the next version of Clang. And GCC didn't even try to attempt a modularized standard library implementation. The next thing that I've been already alluding to a little bit, this is how to make sure that you can use existing BMI files in your code. If you import a BMI file, the interface of a library, you need to make sure that you have matching compiler flags so that you don't run into subtle ODR violation. This is what modules are all about. MSVC doesn't have that many compiler flags that need to match up. It's only these four here, and even then you can decide, for example, I don't care that much about RTTI and can just say, I don't care. This is possible with MSVC. Clang, on the other hand, has an implementation of modules that is mostly built on top of precompiled headers, and therefore it requires a lot of matching compiler flags so that a BMI is actually usable. And if you have a mismatch in compiler options, Clang will refuse this particular BMI to import into your own translation unit. GCC, there is no documentation about this kind of stuff, so I unfortunately have no option to tell you more about that. Next, the hot topic of file naming. There are strong opinions in the community. Some people say modules are broken from the very beginning because every implementer has chosen a different preferred file extension. Yeah, to some extent this is right. This is unfortunate, but it affects you only if you compile manually on the command line. If you use the preferred options here, like CPPM, CPP, or IXX, you can actually compile complete programs from the command line in one go. This is possible, but every compiler needs a different invocation and a different file extension. In general, this doesn't affect you in any way. You use a build system. This is what you do. You don't do it manually. If you want to learn, possibly then manual compilation is a thing. I wouldn't do that. And you need special compiler flags to say, okay, this particular translation unit is a module translation unit or is a header unit, but usually you don't do that by yourself. It is done by the build system. Okay, this is where module implementations are today. Let's get practical. Let's take an existing library, apply all the knowledge that we've learned so far, and make it a module. My example here is the so-called argparse library. Later on in the demo, I will use this particular module. And let's try what we have to do to actually make this traditional header-only single-file module library into a module. And this library is just one namespace with a couple of implementation details and a few entities that are part of the actual interface of the whole library. So this should be easy, right? Does anybody see a problem? I hope not. So if you're an aspiring module developer, you need to do two things. You need to mark it as a module translation unit. You give it a name. And the second thing is you need to mark your interface as exported. Let's do that. Here's the module declaration with the name. And here's the export. We export a whole group, and this is the stuff that you want to export. Easy. Let's compile. In alphabetic order, let's start with clang. This is the most recent clang. It requires a couple of compiler options. Don't even try to remember them. The build system should do it for you. But this is how you would do it from the command line, or I did it from the command line. Let's try to compile the interface. Oh no. Bad. It doesn't compile. It tells us something about the algorithm header. I was using the libstd.c++ standard library here. We have more compilers. Let's try GCC, the latest one. A different set of compiler options, same result. It doesn't compile. Yet again about the algorithm library. I think the plot thickens. Last compiler, MSVC, also the latest one, different set of compiler options, and it compiles. It creates the BMI, the IFC file, and it creates an object. But it has an opinion about this particular code. This sounds a little bit fishy. What's going on here? The include of the algorithm header seems erroneous. It gives actually a hint what to do. You should probably put the algorithm header elsewhere. This global module fragment. That's the solution. Let's introduce a global module fragment. And this is the place, as we've learned before, where we place all the existing library interfaces that come from the implementation or from your code. All of that needs to go into the global module fragment. And please don't forget one. All of them should be there. Don't put them into the module purview. Okay, let's try again. Once again, clang, GCC, and MSVC. Nice try. Clang does what it is supposed to do, MSVC as well, and GCC has an opinion. This compilation is probably worth a segmentation fault. Okay. 1 down, 2 to go. As shown before, the module interface has 2 different interfaces. One that is looking into the module. This is where the implementation files reside. And it has a different interface that's looking towards the outside of a module. If you compile a module, in particular one with more translation units than only one interface, during the compilation of the module, you already exercise the internal interface. You're pretty sure everything is there if the compilation succeeds. But you need to explicitly test the interface to the outside. If you fail to do that, you will probably have problems later on. Okay, I have a very short, very lacking test case here. It doesn't use anything from the standard library. Let's try to compile that. With clang, MSVC, and of course GCC is out. And as we can see, it works. Yeah, with one caveat here. MSBuild requires you to use a particular include from the standard library. And this is actually correct. I've shown earlier, the module has a purview, and this is where everything belongs to that is part of the module. We also learned we have a global module fragment where, for example, the standard library includes live. The global module fragment is a part of the global module, and the global module is a different module. So the standard actually requires you to throw everything out of the global module fragment that is not referenced from the module contents itself. This is, I call it GMF, declaration pruning and definition pruning. Clang hasn't implemented it yet, so it puts everything that it sees from the global module fragment into the BMI, so you get quite bloated BMIs in the current implementation. This will change in the future. This sounds a little bit difficult for users, but modularized standard library to the rescue. You don't care at all if you use that. Okay. This was the easy part. The more difficult part is that I have avoided so far. In the not exported parts of the ArcPath library, there are entities in here which don't have namespace qualification. And this means two things. The first one, all of these names in here are subject to ADL, argument-dependent lookup. This slows down your compilation, not only in modules, in all of your code, by the way. And it can cause lookup failures in case of modules. These are entities that are not exported, and you instantiate a template from a module in your code, and the body of the template wants to refer to entities that are not exported, which means the names are not available for lookup, as I've said before. The lookup will fail. If you qualify all the names, name lookup would happen in the first phase of the compilation during the compilation of the module interface. So you don't have this problem. And there's a different problem in here, so-called translation unit local entities. It's a mouthful. It means you have static variables or static functions at namespace scope in your code, and you refer to these particular namespace static local functions or variables through other functions that are possibly inline or inlined in templates. And this means they have no symbols, and if you compile it in your code and want to refer to them, the linker would refuse to. There are no symbols at all. This is called an exposure. This is actually something that makes your program ill-formed. So you should no longer use any statics or anonymous namespaces in your module code. Please avoid that. And actually, in your current situation of traditional compiling, this is also called out by the standard as deprecated. You should avoid it as much as you possibly can. Don't do that, and you have an easier time to go to the modules board. Let's switch from the smallest module to the largest one in the demo code. I use the ASIO library. This is a huge library, has a lot of files. And if we want to modularize that, we cannot do it in the intrusive way as I've done it with ArcPath. There's a different way how to modularize the library that I call this trinity of modules, the global module fragment, the purview, and the private module fragment. In the global module fragment here, I place everything that comes from the platform or the outside of the library. Then I place everything in the purview and export it from there that are the interface of the ASIO library, possibly even more. And then in the private module fragment that is not visible or reachable from anywhere outside, I place all the implementation files of the ASIO library. This is just one file that I have to compile and get the whole of the library. I get 2 artifacts, the interface and the complete implementation. Okay, this was about modularizing existing libraries. Let's talk about build systems. Build systems should be aware of modules. The oldest one is Build 2. I wouldn't recommend it anymore, but a couple of years ago it was the only one. Then, of course, the most interesting for probably all of you is CMake. It has actually acquired support for named modules, at least since the beginning of the year. But it has no support for header units, and this is a little bit sad. And it requires quite recent versions of these 3 compilers here. Then we have MSBuild. Okay, this is part of Visual Studio. Microsoft has a good implementation of modules, so it has a perfect implementation of a build system. It's boring. It does everything what you expect from it. And then there is a new one called CMake. You might have heard about it. It's quite popular in Asia, and it claims to have decent support for modules. I haven't played with it yet. You can do it by yourself. The best benefit is probably it claims to have a nicer syntax than CMake. Speaking of CMake, the support for modules started in version 3.25, and it has been experimental until 3.27. And back then it supported only Clang and MSVC, and 3.28 with full support for modules. It will also support GCC when it comes out next year. It heavily depends on dependency scanning. This is what I've probably been alluding to earlier. You don't want to do all this dependency stuff by hand, because every BMI is a dependency on the build of another translation unit, as you probably have seen and noticed. You don't want to do that by hand. You want to do that you can offload everything to the build system, and you need either Ninja or the MSBuild as something that executes actually the build graph. So what is needed to make modules, module translation units, and build them with CMake? What you have to do is you need to indicate the nature of every translation unit. This is what you already know. We have a target sources statement, and you place all the non-modular translation units in here. But you also need now a file set. This is a new feature that says, okay, this is a set of translation unit source files that are named modules and create BMIs. And you have the same for header units, but unfortunately, this is yet to be implemented. So you can't use header units yet, but this is what the syntax will be. And you don't have to forget, you need a recent version of CMake with the right policy in there. If you have the opportunity to use CMake 3.28, everything is easy. You can use it also with earlier versions of CMake. You need a little bit more code. You can look it up in my demo sources. As said, CMake depends on dependency scanning and module dependency discovery. So You need to have a compiler that has a dependency scanner in its implementations. All of them have right now. These compilers need to report a dependency that they have discovered. CMake will generate module maps out of these reports. And a module map is something that we will see in the next few minutes. And you need a build node processor like Ninja and MSBuild. These are the things that you need to do. And you need a supported version of CMake, of course. That's a lot you need to know about build system, in particular CMake. Sounds a little bit scary, but please, this is just unfamiliar. It will come quite naturally if you're more into using modules. So please don't feel scared by this guy from 100 years ago. Let's move on to module dependencies. What does it mean? This is another module from the demo code here. This is one that is coming from the SDL library. I don't know how many of you are aware of this library. This is a C library, and I've added a C++ module interface on top of it. And because this is a C library with a lot of macros in the interface, I had to implement the module a little bit more complicated. Now we have not only the module interface in the top left. In the import, in the interface, we also have additional module partitions. These are one of the types that I've been showing before. One of the partitions is on the bottom left, and one is in the middle. And this is where the magic happens. And with the help of a little bit X macro wizardry, I can get rid of all of the macros that are coming from the C headers and turn them into proper language entities that you can export from a module, so you no longer need macros. But this means we have an internal structure of module translation units, not only one, but 3 in this case. So what does module dependency scanning do? In this particular example, I use clang and ask it to create a dependency report for this particular module partition here. This was the one from the bottom left. And clang will then report, okay, this translation unit provides a macro with the logical name SDL partition global macros. This is an interface, and the source code is here. And to compile it, you also need another module partition in this particular case called SDL partition with macros. This is what all the compilers will return if you ask them to do a dependency scanning and reporting the results of it. This is from Clang. MSVC is just the same. Small differences, but all the interesting parts are identical. And what CMake will then do during the compilation, it takes all of these reports and creates so-called module maps. Sounds pretentious. It's nothing but feeding the correct compiler flags, where to place the output, where the BMI should go, where to find referenced BMIs from other modules. On the top with Clang, on the bottom with MSVC is just the same, but different syntax. And this is what a module map is all about. You don't want to do that by hand. And this is the important part. Use a build system to just forget about all of that. This is what's going on behind the scenes. If you are a Make user, you need to know about all of that. Okay. Now we know everything about modules, how to modularize old code. what need to avoid to not run into pitfalls, how to use the build system with modules. Let's do a short demo. That is not just a promise, but this is reality. And the demo code is the same as I have been using it last year. Who of you have seen any of my talks last year, the keynote from here, or possibly the keynote from CPPCon? Good. But there's a lot of people who haven't seen it yet. So this demo code is a small application. It consists of two parts. One is the client part and one is the server part. These two parts speak over a network connection. And as soon as the client connects to the server will look into a certain directory that is given on the command line to look for animated GIF files in that directory. And it would then decode this GIF file into video frames and sends each individual video frame through the network connection to the client. And the client would pick it up and display it on a GUI. This is what this application is doing about, and it does it endlessly as long as the client is connected. If you want to know more about this demo application, watch the keynote from last year. This main translation unit here is the only one that is not modular. It uses only modules, the modularized standard library, the ASIO module that have you seen before. It has a couple of more modules that are coming from the implementation of this application, and then a few lines to orchestrate all of the services that come from the modules in the application. This means this application has a certain module structure. Some of these modules come from the implementation of the demo code itself, 8 named modules. And these are deliberately made so that you have every translation unit type that you have seen in the table before. So you can look it up and see how these different translation unit types can be applied to in practice. I have a header that has formerly been a header unit, but because CMake doesn't support header units, unfortunately, now it's a header again. And it uses third-party modules as dependencies: ASIO, ArcPath, libav, and SDL. We have seen 3 of them before. And it uses the modularized standard library. We know libs.c++ has not a modularized standard library yet. libc++ is not yet published. So I had to do my own implementation of a modularized standard library with some additions on top of it. And this is what I'm using here in this demo code. So, let's get real. Let me start up Linux. Come on. Here we are. I've already pre-configured this whole application. It takes a long time, unfortunately, on Linux for reasons. Clean it. So we do a full build. What it actually builds is all of these modules that we've seen in the previous picture: standard library, the 4 external libraries, everything within the demo application itself. And now we're done. Everything is compiled. Did anybody of you notice any delay because of compiling the standard library? I hope not. And okay, it did build. Let's try it. Okay. Last year, you've seen it on Windows with the Microsoft compiler. This year, you see it the same, running on Linux, built with Clang, and ellipse.c++ standard library as a module. I think this is quite encouraging. So what is my conclusion from all of that? Even if you don't want to use modules yet, I highly recommend to use the modularized standard library. You didn't notice any build delay, but using the modularized standard library gives you huge benefits. In the code on the above, you see 3 methods to provide all API of the standard library. You can use an umbrella header, like all.hpp here, and textually include it, like you always did. You can use this umbrella header and compile it into a header unit and import it. Or you can use the standard library as a named module and also import it. All of 3 options are available to you. You can also use them all together, and this is supposed to work, the standard guarantees. So if you only include the umbrella header by itself, textual inclusion, how long does it take only to bring in all of the API without any further compilation? On my test system, it takes a little bit more than 2 seconds to actually just provide the API. If I import it as a header unit, I measured 15 milliseconds. And if I import a proper named module, I can't measure it. It's impossible. No matter what I did, it was every time less than 1 millisecond. I think this is quite a feature. And this matches up with what I've been showing 2 years ago in a different talk. I did it with the FMT library in 2021. As you can see, header-only textual inclusion can slow down your compilation quite a lot, whereas just importing all of the interface, in particular of the FMT library, it's unmeasurable. It's just the same as with the standard library. So, use the modularized standard library if anything else is too much for your current situation, but I highly encourage it. And looking at everything that I've shown before, what's my opinion on that? Well, it's like this. I think we have come a long way with module implementations. Now you can do it on multiple platforms with multiple compilers. And this actually works. Modular, the regular implementation bugs, but besides that, you can actually do interesting things with that. And if you want to use modules in the future, this is probably about the time where you can start experimenting and getting your own experiences and how it fits to you and your particular situation in the company where you're working at. I started using it in production 2 years ago, so I think you can do interesting stuff. Here you can find more resources about modules, about the code that I've shown before. Here's the QR code once again, where you can get all of that, including the slides. And you have a little bit of contact information if you want to ask me questions beyond the end of this conference here. And with that, I'm done. And if you have any questions, feel free to come up to the microphones. Hey, come on, guys. Are you scared? I hope not.
Well, not from you, but from modules, maybe. So if I have a large application code base and I want to move towards modules, would you think it makes sense to make an intermediate step with header units?
It depends on your build system.
CMake.
Okay, now the question is answered.
Well, waiting for CMake with header units.
Come on. CMake with header units. Oh.
Well, waiting. Or is it a long wait, do you think?
You notice I'm a member of the tooling study group in the committee. We are discussing this stuff quite a lot. If you really want to use header units, you probably go with MSBuild. If you need to use CMake, you probably have to wait for, my expectation is a year. Header units seem simple. They're actually the most complicated thing in the world of modules. Most people underestimate what it takes to use header units. And it was advertised as the intermediate step, as you were saying it in your question. But actually, it's a dead end, in my opinion. I wouldn't use header units unless I'm really forced to. Maybe you have macros in your interfaces, then there's probably no other choice. But then you have to wait for a build system that actually supports it. Maybe CMake is a solution for you.
Okay, thank you.
Welcome.
Hello. I would be interested if there are any implications on shimming. So if I preload my custom binary to override some routines, and if I have implementation in a certain module, would I need to have shims that reflect some sort of routine or function names then in the resulting assembly code?
Excuse me, I didn't really understand everything because of...
Yeah, so if I want to override routines by using a shim and preloading a binary, are there any namespace or name implications when I use modules?
In general, modules don't change anything of that per se. Modules are about the interfaces. Implementations don't change at all. You have to make translation units of the implementation parts of a module just to contain the name, but besides that, it's just the same. You can use DLLs, you can shims, you can use anything you like. As long as you don't run into ODR violations, you're good.
Okay, thank you.
And everything else is unchanged.
Great presentation, thank you. When would you guess, realistically, pessimistically, GCC and Clang would catch up with Microsoft?
Good question. It's very difficult to answer this question, like we learned in the keynote in the beginning, predictions of the future are difficult. So, what's my opinion on that? Well, we see implementation bugs and deficiencies in implementations, both with Clang and both with GCC. I think Clang is on a very good trajectory. Speaking with the Clang developers, I would assume Clang 18 is a huge improvement over Clang 17, just like 17 was an improvement beyond 16. But it's a matter of prioritization. What's more important for the implementers and the people actually behind the financing of the work on Clang? On GCC, well, I think, at least I hope, GCC 14 will be the very first one that's actually usable for some light usage of modules. I think GCC is at a situation where MSVC has been 2 to 3 years ago, and MSVC has good funding. GCC doesn't. Draw your conclusions from that. So I see, if you want to use modules in a good way, without too many hassles and too many bugs, beyond Windows, I would highly recommend go with Clang. And I think beginning next year, we can expect Clang 18. First quarter. So this is probably a good way to do more serious work with Clang in the world of modules. That's my opinion on that.
Thank you.
So I was told I can't tell you any more, but you will find me on the rest of the day in the conference and ask questions, form opinions. Thank you for your attendance and your patience.